They died or ain't turn around backwards.
All right, what we're talking about here is electrical basics. If I can get this thing to operate. Will that work? I may have to do it manually because my batteries may be dead and I removed it. All right, you know everything is fixed. I'm gonna go through this pretty quick so you guys pay attention, right? Okay, everything has got liquid or gas is made up of little particles called atoms. Now, a lot of the time, what we don't realize a lot of times is what they don't show us when they're drawing pictures like that is that these particles are a long way from that nucleus, right? And so you got protons and neutrons in here, you know, electrons around the outside. Now, in this picture, this is not really accurate because electrons are really, really, really small and the protons and neutrons are larger. So if you've got you got an outer electron, see the free electron? That's the valence ring. And if you've only got one free electron, then it's a good conductor. If you've got 8, it's an insulator, which would be glass or something like that. But if it's only got 4, it's a semiconductor, which is what they use to make transistors and diodes and stuff like that out of it. It would be like silicon or whatever. All right, they are known as bound electrons. The ones on the inside don't move. The ones on the outside, in the outer orbit, those are the ones that move. Now let me ask you this, where does the wire travel on a wire, on a copper wire? If it's traveling down that copper wire, where are those electrons traveling? Not through the middle, they're traveling around the outside, okay? They're called the valence ring, the ones on the outside. In other words, kind of the outside of the wire. Just remember that. The outside of the wire carries the electrons, the inside of the wire does not. The outside of the atom carries, you know, the electrons jump from one atom to another. And those are called free electrons. If there's 3 or less, it's a good conductor. Gold and copper only have 1 electron in their valence rings, and they're really good conductors. Some of the other metals have a few more, but 8 is as many as you can have, and you can't have less than 1. A material with exactly 4 electrons is a semiconductor, which is the stuff that's used to make, you know, diodes and transistors. And a valence ring with 5 or more makes a good insulator. So if it's got between 5 and 8, it's a good insulator. Electron theory says current flow is the organized force movement of electrons in a specific direction. And so if you're thinking working on your car, you're thinking its power starts from the battery and it goes from what? Which way? Positive to negative? We're going to start checking that way. Basically, we hook our test light on the ground and then we're looking for power everywhere, right? Of course, there's sometimes you need to flip them around and look around too. But electron theory says that, the electron said that power flows, the electron flow is from negative to positive, because electrons are negatively charged. The positive to negative is conventional theory, is what they call it. All right. Okay, so direct current is when it's only flowing in one direction. That's like on your car or a battery or something like that. What's coming out of the wall is going back and forth. You know, that's your alternating current and all that. A good conductor is a material that's got a lot of free electrons, copper, lead, gold, we've got large numbers of free electrons. And so what I mean by that is, you know, you've got them all able to move there. All right, and they transmit electricity, that's not too hard. Electromotive force, that's a term you need to be aware of. And there's going to be a word I'm going to give you in here that you're probably never going to hear again, you're never going to use again, but you need to hear it one time anyway. Electromotive force is the difference in electrical potential. So basically when you're charging a battery, and I'm going to try to make this as simple as I can, the battery charger is basically an electrical pump. If it's an alternator or whatever it is, and it's going to take the electrons from where they want to be to where they don't want to be. And they're always wanting to go back. You got me? They're going to find a way back. So if I pull the electrons, let's assume that it's taking the electrons from the positive side of the plate and putting them on the negative side, and there's a tension there. It's like stretching a rubber band. Where does it want to go? It wants to go back. So charging a battery is like stretching a rubber band, and then there's work that can be done if you hook something to that rubber band that can be moved. You ever made one of them little tractors with a thimble and some couple of toothpicks where you can wind it up? You've done it, haven't you? And then you just, when you wind it up and you put it down, it goes scooting across the floor because that, you know that. But anyway, that's kind of like what you got going on there. Craig Van Vattenberg liked to teach this as army men. That all the army men that leave always come back home. You know, and they, you know, they're never a wounded army man. And if there's resistance, like if you got rocks and stuff in the road they got to walk over, They can't go through there as quick, and they got to work harder to get there, and it heats them up. All right, so you ever play pool? All right, you put a bunch of balls like that together, all of them touching. If you hit that with a cue ball, the 8 ball takes off, but the rest of them just sit there. Right? That's how that works. The electrons start to flow. It's the same way, all along the conductor. And here's something else I want you to burn in and remember. Current flow stays, and we talked about this a little last semester, the same throughout a circuit. You got amps flowing from positive all the way through the load, all the way back to your negative. Anywhere you hook up to that circuit, you're going to find amps. But because ground is your reference point, you're only going to find voltage on the positive side. Right? So just remember that if you start checking voltage on the negative side, unless you swap sides and hook your test light to your positive, you're not going to read anything on the negative side. All right, so some older, like I worked on some heavy equipment in the 70s down in Texas, and Caterpillar equipment, and I don't know how they do nowadays, but Caterpillar equipment in those days, these big pipe loaders and stuff, had positive ground. Now, if I pull a positive ground pipe loader up to a negative ground pipe loader and I want to jump it off, is that a problem? Only if they're touching. Doesn't really matter because it's still positive and negative. But as long as the frames of these two machines aren't touching, that ain't a big deal. But if you get your jumper cables hooked up and somebody moves it over so the frames touch, you got a big spark. Because positive ground, see the whole frame's lit up and ground's the other side. That's the Caterpillar way of doing that. And we had International and Caterpillar. No production vehicle uses this today. Everything has got negative ground. Now, eons ago, I heard about this guy that was trying to work on his vehicle. It was an old 49 something or 50, back in the 50s. And when you try to start it with the key, it wouldn't start. But you could push it, and as soon as you let off the clutch, it would fire up because it was, obviously standard transmission. And there was an old drunk that was always hanging around the shop, and the guy was working on it, trying to scratch his head, trying to figure it out. And the guy said, ground the motor to the frame, ground the motor to the frame. And he said, what are you talking about? Finally, he got some jumper cable and hooked the motor to the frame, and it fired up with a key. So he had a bad, ground is what it was. And that guy said he had seen that before, All right, so most of them got their negative, the frame is where the ground is. And your ground symbol looks like that. See how that ground symbol looks? Your car chassis, that's the reason that we draw this way, is because our ground is connected to the car chassis. And I will tell you that some of your wiring schematics, like on Mazdas and all, they'll have a line along here, and they'll have a little symbol that looks like a car. And that's supposed to tell you that that's the body of the car. Now in this particular case, we're just going to show it like that. And then you got your switch, your hot wire, your load, and all that kind of stuff. All right, when a switch is closed, current flows. You got to have a ground, you got to have good voltage in your battery, you got to have your switch closed in order to do that. That's actually a closed circuit. And once again, the amps is going to be the same all the way through. But the only place, because you're measuring from here, the only place you're going to see voltage is over there. I'll be using my laser instead of my finger, I guess. All right. Even though the ground has the excess of electrons, the positive post is the one that's generally regarded as hot. You all know about that, right? All right, electron theory supposes current flows from negative to positive. That's what I was talking about a while ago. Remember that. Electron theory supposes current flow from negative to positive. And when a wire or something gets hot, it typically has more resistance or less resistance? More resistance, and that's what you call positive temperature coefficient, like light bulbs and stuff. The current in automotive circuits is traced from the source to the load to the bulb. Basically, if this didn't work, where would you start? I've got my test light in my hand. I'm going to use a test light. I mean, a lot of the instructors don't like test lights, but I got in a mess one time using a meter to check the anti-lock brake system on a Taurus there when I was working at the dealership, and I was going by the book and it said get a meter and see if you've got more than 11 volts here. So I checked it and I had more than 11 volts. And I went all the way around Robin Hood's barn. Then I found out this more than 11 volts I had here wouldn't burn a test light. A meter will lead you astray if you're measuring something. Now, don't use a test light on throttle position sensors and computer circuits that are actually sensor circuits. But if you're measuring something that's going to pull a load, you better be using a light bulb or something that'll pull a load to do it. That's all there is to it. Anyway, so if I'm going to do this, what I'm going to do, I'm going to take my test light and I'm going to hook it up over here, and I'm basically going to start right here, and I'm going to see if I can power right there. Now you can hook it up, if you can measure from here to here, that's perfect, because you're measuring all of this automatically. and you're seeing the ground too. So if I got power and ground at my light, then I know I got a problem. If I just measure it right here and I don't find any power, if my test light don't light up there, I still got to go find out where it is. If it's bad switch, or if it's bad connection here, bad ground, whatever. You know, that's where we're headed. This is the way we start out. Now right here, you see all this? See your negative plate? It's a number of positive plates and equal number of negative plates, and they travel through this electrolyte. Now, do you guys understand pH? You know what pH is? You ever hear about pH when you're talking about measuring water?
Just the acidity of the water.
7 is the middle, and when you go down, you're going acid. When you go up, you're going alkaline, right? Have you ever noticed how the batteries in a car are acid and the batteries in your flashlight are alkaline? They're both out of balance, and when they're out of balance, current tries to flow. So that's why is that you can take a weak light bulb and stick it 2 wires in with it hooked up into a lemon, and it lights that bulb because it's acid, right? Isn't that something? All right. So positive and negative plates are immersed in electrolyte solution as water and sulfuric acid. When the battery is charged, the chemical reaction results in the excess of electrons collected on the negative plates. So you charge it, and basically, like I said, it's like a pump. You're putting all those over, and they want to go back. And anything that you put in between there is going to be a load. What happens if you put one of these jumper wires in? Who in here has burned up a jumper wire or two? You hook them up, smoke goes out of the jumper wires. I have to buy new jumper wires all the time because I've burned them up myself.
I burned them up plenty of times.
Yeah, and so basically, and it stinks up. And one wire this long, burning under the dash can fill the whole cab of your car up with smoke. Make you think you burned up a whole daggone wire harness, and then you just burn one little short wire. Just scare the daylights out of you. But that smoke is poison, so don't sit in there breathing it, okay? All right, so this is induction. When a conductor in a closed circuit is passed through a magnetic field, you create current. Okay, I can take me a magnet wire, and I got a roll of magnet wire out here, and I can roll it up and roll it up and roll it up and hook up both sides to a meter, and then I can make it like a donut, and I can take a magnet and go through that. Don't even touch it. I'm just going through there, and you're going to see that meter going back and forth. Because that magnetism is going to create, that's how an alternator works. That's how these sensors work. Like on that thing right there, you get a little magnet in there. If you get an iron core, it makes it stronger. All right, so the magnet wire is not just copper wire. This wire right here is not just copper wire. It's copper wire that's coated with something so that the loops don't touch each other. Because they don't want it jumping from one loop to the next, and if it does, it's shorted and it's no good. But if it's going around and around and around and around, it creates a really strong magnetic field. And that's what the deal is on that. All right, alternators, generators, and inductive sensors use that to work. So if you walk on the carpet, here's another thing you might not know. If you ever walk on the carpet and shock somebody, you ever do it on purpose? Just reach out and pop them on the nose or whatever. That's from 8 to 25,000 volts. Think about it. Now, you're probably not going to hurt anybody by doing that. You may make them mad and get your nose punched if somebody's in a bad mood and all that. But the thing about it is, you can damage electronic components that way. Or you can set yourself on fire at the gas pump if you're not really careful. That's why have you ever noticed the sign on the gas pump that says always put the gas can on the ground? Because if you're up in the truck and a static discharge happens, see, because it can make it catch fire, and I've known of that kind of thing happening. Poof, all of a sudden there's a big fire in the back of the truck. Somebody gets burned and all that. But you set that gas can on the ground when you're putting the gas in it. Don't put it don't leave it sitting on your tailgate. That's a bad plan because of static electricity. All right, lightning is another form of static electricity from the atmosphere to the earth. Now then, let's move on to this. So electrical current is a complete path for current flow. Complete path is going all the way around, right? Power source, load, component, resistance uses the ground path. Resistance is where work's done. Basically, it's going to make motion, heat, light, magnetism, that kind of thing. All right, you got to have a battery there. That's a schematic symbol for a battery. Remember what a battery looks like. That's what a battery looks like in a car, as if none of you boneheads haven't seen that, okay? The power source is the battery, the engine switched off, and the alternator. In other words, when the engine switched off, the battery is going to be your source of power. So there ain't no power nowhere else. I got in a car one night whenever I was driving over to visit the boys. We were out there at a ballpark throwing footballs around and stuff. We got back in the little car I was driving at the time. When I turned it, the battery exploded. when I tried to start it. I heard boom under the hood. I opened the hood, and the battery's all in pieces laying all over the place under there. We had nothing. You know what I mean? So you gotta have a storage component. You got a battery that's coming out of the loop. In other words, for example, if you've got really, really, really dirty terminals right here, you can actually get a car that'll just quit running because of dirty battery terminals going down the road. You know? All right, there's your conductors, your wires, your cables. They got installation on them. You've seen that. And the colorful installation is really, really handy. You notice how this wire right here is twisted around itself? That wire is typically done that way so it won't have interference from other circuits. Because whenever you've got a lot of current flowing through some of these other ones, it creates a magnetic field. And if there's another one laying next to it, like spark plug wires, on a 350 Chevy or a 302 Ford, you can actually run your spark plug wires, you know, to 5 and 7 on the Chevy, you know, or 5 and 6 on the Ford. If you run them right next to one another all the way to the plug, the one that's firing ahead of the other one will induce current, or actually a spark in the other one. Even though there's nothing to jump through, it induces it because that magnetism is going to create a spark. Then it can fire, like for example, that the spark plug that's right behind it is going to make it fire early, and it can actually damage things. But that's why you got to run them with a bunch of other wires in between them instead of right next to one another. That's induction. An automotive circuit, the vehicle chassis, and the engine block are conductors in the circuit. Now, switches are necessary to turn the circuit on. There's your loads, motor, light bulb, whatever. Okay, we're moving pretty fast. The circuit protectors are the device that protects the conductors and components in case of an overload. There's your fuse. That's what a fuse looks like, sort of. There's different drawings for fuses, but that's the fuse. Current will flow if the switch is closed, the circuit protector is not open, and charge is available. In other words, charge being battery power, your electromotive force. Now get used to this Ohm's law, because everybody needs to know this. I'm going to tell you something. You probably won't ever use Ohm's law working on a car, but if you don't understand it, you're going to be handicapped. Okay, so we go through this. Just remember it, because you're going to need to know it for some of your exercises and stuff. Current flow is directly proportional to voltage. The more voltage you put out, the more current flow you got. All right, how many of you guys know, you ever, when you're getting an air conditioning unit, like if I was going to put a window unit in this room instead of using the central air, if I got one that was 10,000 BTU and I got one that was 110, or I got one that was 220, it was up to me, right? Like maybe if I could use either one, which one would you rather use? The 220 is the one you need to use, and the reason you need to use that is because it only uses half as much current. More voltage means it requires less current to do the same work, okay? Got that? That's what we're talking about here. You may be seeing these stuff on your paper already. All right, an increase in resistance will cause a decrease in current flow. If you change the amount of resistance, if I put more resistance in a circuit, then it's going to be less current flowing through the circuit because of the resistance. So the resistance impedes current flow. What else happens when you have resistance? Why are resistors made of ceramic? Because they get really hot. Where you've got resistance, see these resistors right here? These resistors right here came off of a fan on an Oldsmobile. Like, you know, sometimes when you want to lower the speed of the fan for whatever reason, you know, you get this resistors right here. Whenever you run the fan through these, it slows the fan down. There's no resistors on this board here, but we can run it 2 speeds by wiring them in series one way. But when you put a resistor in there, these things are heavy-duty ceramic, because if they happen to be flowing current through that thing and you touch one of them, you're going to know it. Because it'll lay a clear blister on your finger when these things are good and hot.
Hey, you got some.
Yeah. Hey man, got all your stuff? Okay, just wait until, just hang out and Joe and these guys right here are doing it all the way doing it fast. You can wait wherever you want to be. Couple of new guys. All right here, that means resistance will, all right, let's do this again. Okay, this is Ohm's law. High current flow, I put my boot on there, and it slows it down. So you got more there, less there. So consider that resistance. I always like to use water to do this. Other people do it other ways. All right, now watch this. This is important. Some of you guys don't grab it. E is the volts. I is current and R is resistance. Can you memorize that? The EIR. Remember, I is current, R is resistance, and E is voltage. This is electromotive force. This is resistance. If you can remember that R stands for resistance, you can remember that I stands for amps. I don't know why they chose those three letters. I guess I could probably researched it and put it in my nifty little presentation here, but I didn't. All right, 1 volt pushes 1 amp through 1 ohm. So how many amps will 12 volts push through 6 ohms? 2. 2 to 6 is 12. Got it? 6 into 12 is 2. 2 into 12 is 6. Got that? That's really simple, isn't it? Now there's some really complicated charts like this that you can make that goes just way off out in left field, but this one here is a really simple one. That's, you know, little equation there. All right. All right, voltage is like pressure. All right, look at this. 10 volts, you got a weak battery here. Current draws 5 amps, resistance is 2 ohms. But when you got 12 volts, you got more current going through there, resistance is 2 ohms. All right, resistance 2 ohms draws 5 amps. 2 ohms draws 6 amps, it's the same deal. Increase in voltage in a given circuit always increases current loss. If the only thing you change is the voltage, when you go up with the voltage, you're going to have more current draw. That's just the way it is. All right, voltage is also expressed as the difference in potential when it refers to electromotive force causes electrical charge between 2 points in a circuit. All right, so you got 12 volts available here, 24 volts available totally, but the 12 volts is potential. Why is that? What you got 24 volts here for? You got your positive and your negative connected together. See that? All right, and so if you got ground here and you're measuring there, this is 24 volts because you're stacking them together. How's a 9-volt battery made? The one like the little 9-volt battery? You know, the one you stick to your tongue, you go, ooh, ow, that one's hot. Remember that one? It's got 6 1.5 volt batteries wired in series on the inside of it. If you ever take a 9-volt battery apart, you'll find 6 small batteries in there. That's how they do that. Just like you're seeing your vehicle batteries got 2-volt cells, 6 2-volt cells. And, all right, current flow. Load A, 6 ohms. Load B, 12 ohms. This one draws 1 amp, that one draws 2 amps. You notice that? Now look at this right here. This right here is what you call a parallel circuit because each bulb has got its own ground. You got it? So if you lose that ground, this bulb still works. If you lose that ground, this bulb still works. This is a parallel circuit. Remember that. Basically, they got power going to both of them, and each one of them got its own ground. Now, that's something you need to soak in. I'm going through this pretty quick so you don't go to sleep. All right. The unit of measurement to determine current flow is called amp. That's abbreviated, you know, ampere, amp. Now look at this. This is a word I was talking about you'll never use again. 1 amp is defined as the movement of 1 coulomb of electrons past a given point in 1 second. A coulomb is 1 billion electrons. Can you remember that word? Coulomb? C-O-U, I might not even be saying it right, see it, but I've never used that word unless I was doing this presentation. But that's what 1 amp is. 1 amp is defined as the movement of 1 coulomb. Current is a measure of rate of electrical flow, can be known as amperage draw measured with an ammeter. And when 2 loads are connected parallel, each draws independently of the other. So your total draw is 3 amps. 1 amp, 1 and 2 is 3. That ain't complicated. All right, the picture bulb draws A amp, B draws 1 amp. Okay, let's go. The total current, now listen to this. The total current draw in a parallel circuit always equals the sum of the two. 1 and 1, you know, 1 and 2 is 3. Don't get confused by those words. But look at this. This is a series circuit. 6 and 12. 0.67. See that? It's having to go through all of those. So the combined resistance, you add these resistances when you're in series. You got that? So it's 18 ohms, and if you take what you got, 18 ohms, and divide it into 12, and we're going there for 0.67 times. That's what that is, see? And that's what that looks like. See that? 18 into 12 is 0.67. So that doesn't even equal 18. All right, there's your resistance. So resistance is opposition to current flow, load or resistor. Conductors have some resistance. Pay attention, I think that's questions on your test. A 22 gauge piece of copper wire 60 feet long has 1 ohm of resistance. Larger diameter wires have less resistance. Heat causes resistance to increase in a conductor. Now this is actually, this came off of a vehicle we worked on. And you're gonna see this if you work on stuff very much, where there's the most common things that you're gonna see this on, most common stuff, you're gonna see it on fans. Because fans pull a lot of current, because fans have to move air, and air is, you know, heavy and all that. Well, what happens is, these terminals start to oxidize a little bit. When they start to oxidize, they get resistance. When they get resistance, they get heat. When they get heat, they oxidize more and they get more resistance. And finally, you have a meltdown like this, and it totally stops. This is a blower motor relay from Pontiac, Montana. I mean, or Oldsmobile Silhouette or something. But anyway, the thing about it was the fan wasn't working. When we unplugged this, this is what we saw. In this case, you have to replace the connector, and you got to replace the relay.
That's what happened with my blinker. I never replaced him, it's still causing it to melt.
Yep. Well, if it's pulling too much current for some reason, some other reason, it'll do that too. And so, but anyway, yeah, and that's what happened. Every connection, you know, the heat produces more resistance. If you've got, there was a GM instructor one time where, you know, that my buddy Donnie here, he went to a GM school, and that guy said that when you unplug connectors on a GM car and plug them back together 4 times, you're probably going to start having trouble with them. Because they're not really made to unplug and plug them back in very many times. The first time they're plugged in, they got the best connection they're ever going to have. And sometimes it ain't that good. And here's another thing. Don't take a test light when you're checking a connector and ram it down in there so you spread the terminals. Don't ever do that. Because when you do, when you plug it back in, you got this and it's not even touching, or it's barely touching, and then you wind up with this. So don't ram anything down in there to spread the terminal. Just touch it very gently. Or if you can't get to it with your test light probe, you know those little windshield wiper stainless steel strips I get out of windshield wiper blades? You can usually poke one of those down in there and it won't hurt a dadgum thing, but it gives you a good test point. And I always save those things because they're good for all kinds of stuff. All right, so resistance, 6 ohms, 6 ohms, that's 12 ohms, right? But what about this? How many ohms is this going to have? This is important, so pay attention. Don't go to sleep on me. 6 ohms is 6 ohms equal how many ohms?
6 ohms, or you have 6 ohms.
Does it? If I've got 6 ohms, these are parallel now. I'm sorry, these are parallel. See that? It can go that way and that way. But if I took my meter and put it here and here, what would I have?
Wanna be
3. Imagine a bucket with holes in it. If you've got a little bitty hole, that's a high resistance number. Let's say a 10 ohm hole, a 1 ohm hole is really big. A 10 ohm hole is really small. If I've got 2 10 ohm holes, that's equal to how big of a hole? Because you got an extra place, it's equal to a 5 ohm hole. If I've got 10 ohm holes, it's equal to a 1 ohm hole. See what I'm saying? That ain't complicated. Now if you get into avionics, you'll dig into this a whole lot, you know, deeper. But 12 volt supply, how much amperage would each of these pull? How many amps is that going to pull?
6.
No, wait a minute.
Wait, 2.
2. All right, so each 6 ohm resistor will pull 2, and 2 plus 2 equals 4. So this is going to pull twice as much as it would pull if it only had one 6 ohm resistor. If the total circuit pulls 4 amps, how many ohms of resistance would the total circuit have based on a 12 volt supply? 3. See that? So you could use your amps to figure out what your ohms is. All right, let's try a different combination. With a 12 volt source, how much total resistance would this parallel circuit have? Gets a little more complicated, doesn't it?
Mm-hmm.
All right. Okay. 5 amps, 2.4 ohms. Got it? Now, if you ever see that on a test, it always, if you see a whole bunch of them, if you say, like let's say that you see a circuit that's got a whole bunch of resistors in it, always, and they got them all valued out for you, and they say, and they give you a multiple choice. All you got to do is pick the answer that's less than the least, and you'll have the right answer. You don't have to do all the math. All right, so that's 2.4. All right, so voltage measurement with respect, I'm going to show you later, there's actually how you can, as a matter of fact, if I'm not mistaken, you guys have already done this in fundamentals on this calculation of these circuits and all. All right, we'll be through here before you know it. The basic rule for closed circuits, the voltage used up is dropped. See that? You're dropping every bit of it right here. This is going to read 12 volts because you're dropping it all. Now, let me ask you this, what would be going on if this was 12 volts and I was only reading 8 volts?